Three-dimensional trigonometry is a lot of fun, but there's a few things that you need to do to make sure that you can get these questions right. So here's some basic principles. You might want to write these down in your theory book. You need to draw things really carefully when you're working in 3D. And if you're not good at 3D drawings, don't worry, there's a few tips that we can give you to help you. For example, over here I've drawn a square-based pyramid. Now to do that, I've literally just drawn, well, a parallelogram really. Looks a little bit like a square pushed on its side. And then I know it's got 1 point straight above it. So the easiest way to do that, I need to tilt this up a little bit, is to just draw the point and then make that point come down to all 4 corners. So a few little tips like that can help. Now if I wanted to draw the vertical height, pick the point that you think is in the very middle of the base and just join it up. Okay, and so those sort of tips can help you. Now carefully identify which individual triangles you want to work with, because there's a lot of triangles in your drawings. For example, this drawing over here of the square-based pyramid, it has triangles that are made up of the entire faces of the pyramid. They're triangles. They don't have right angles though. If I wanted to make them into right angle triangles, I need to divide one down the middle like this and put a little right angle at the bottom to show that this purple line divides that face into 2 parts. So I could work with either of those triangles. There's also triangles like this big purple one here, which has a right angle. It's between the vertical height of the pyramid and the slant height of the pyramid. I could also make a triangle that goes from this vertical height of the pyramid out to one of these corners. If you can picture this, it's going out to the corner, and that's going to have a much longer base because it's going out to the diagonal. From there I could bring another triangle back and make it have a right angle here to show a plan view, I suppose. And that brings me to my next point, is that if you want to draw it, a plan view can help. So if I picture looking down on this square-based pyramid from above it's just going to look like a square. So if I label some points, let's say this is A and this is B, and this part here is starting to look a bit tricky and I'm thinking this through, well that point right in the middle here is going to be in the middle of the square looking down on it from above. And here's A and B. So if I've made this point right in the middle of A and B, and I've told you it has a right angle, from this view it looks a lot more straightforward, and that angle there is what we're talking about, is this one here. And the triangle that we were building goes from here up. So we've got triangles on the base, we've got triangles on the actual side, and we've got triangles between the base and the vertices. Now, start with any triangle that can be solved. What do we mean by this? Well, if you look at a triangle and you know 2 things about it, you can find the third one. So if you're using your trig, you can find an angle if you've got 2 sides and there's a right angle. You can also find a side if you've got an angle and one other side. Don't forget also, you can use your Pythagoras' theorem in any of these questions, wherever it's smart to do so, and it often is, so that if you've got 2 sides, you can find the third side using that. And work your way to other triangles. So what I mean there is that if you know one thing in a triangle and you can use that to figure out another length or an angle, you can then work your way around to other triangles that have unknowns in them to solve your problems. Now, if no triangle can be solved, form an algebraic expression for a side and work with that. Now, this sounds like a tricky idea. The easiest way to explain it is to actually do an example. So I've got an example over here. I might rub this off. If you want to get this down, just pause the video so you can copy it down. And I'll do our working over this side so that I've got a bit more space. Now, this example is actually in your textbook, but I thought it's a little bit tricky, so it might be best to talk it through. Now, here we've got somebody driving from A to B. So they're driving along in this direction, and I've done a dotted line to show that they're going to keep on driving like that. Now, when they're at A, they look up at a 10-degree angle of elevation. This is 10 degrees here. And they see the top of a tower. This is a tower here. Obviously, this is not to scale. It'd be a pretty tall tower, but maybe. Okay, so they continue driving, and when they've gone 3 kilometres further, they look at the tower again and find that it's now a 12-degree angle of elevation to the top of that tower. Now, the tower hasn't moved, but they have. So we've sort of got a tetrahedron here. If we imagine the plan view, we've got north here because when the question says that when she was looking at the tower originally and saw the 10-degree angle of elevation, she was driving north. And so the questions say, A, how tall is the tower? And B, what bearing is she travelling on? What bearing is she driving on? Okay, so this is an example of a question where we can't answer anything straight up. The reason is we know that she's gone 3 kilometres. So it looks like to find how tall this tower is, the only measurement we've got is down here. And it's not part of a triangle that has H in it. So this idea that you might take this tower and just give it a label. We've called it H here, so that way we can work with it. Now H is part of two other triangles that we know something about. This triangle with 10 degrees and this triangle with 12 degrees. Now what's a really handy thing to do here is actually just redraw some of your triangles. These all have right angles in them. So if I redraw ATF, I have this. I know this is 10 degrees and I know that this is the height of the tower. At the same time, I've also got this one over the other side. So if I draw that separately, make sure they've got a right angle on them. And this one is 12 degrees as an angle, and it's H, and it's TFB. So see how I've basically taken one complicated drawing and split it up into two triangles that are a little bit more straightforward. Now my triangle along the ground, this one down here, I'm going to draw that as a plan view. So when she was looking north, let's make this be north, towards F, when she was at A, all right? And then she went 3 kilometres to B. Hold on a minute, let me think. That's a right angle in here on the picture. So she's gone 3 kilometres, and this is a right angle here at F, and she ends up at B. We want to know what bearing she's driving on. So the bearing she's driving on, if this is north, is going to be this angle in here. So drawing it on a plan view just helps me really work out what I ideally want to know. I want to know H, how tall the tower is, but I also want to know what this angle is here. So let's call that theta, and that's something we want to figure out. Now on this picture you can see I can't jump straight to finding it because I don't have anything other than 3 kilometres. So I need some kind of expression for FA or for FB or for both so that I could use Pythagoras if I wanted to figure out something. So there's a lot of unknowns. You just need to start somewhere and see how you go. So how tall is the tower? Well, I could write here that tan of 10 degrees is equal to opposite over adjacent, H over AF. Now, why am I doing that? Well, I'm thinking that AF and FB are part of this triangle. So let's try and get an expression for AF and for FB, because then we can throw them into this triangle. Now, if I try and get an expression for AF out of this, I'll get this, H over tan 10 degrees. And when I start dealing with that, it's just going to be a bit awkward because it's a fraction. Now, can you remember another function that's like tan, that is the reciprocal of tan? That's right, cot. So I'm thinking of using cot in my expression here because I know that 1 over tan of 10 degrees is the same as cot of 10 degrees. And so it's just going to look a little bit tidier if instead of using tan of 10 degrees, I put cot 10 degrees. All right, let's do the same thing over here. If tan of, if tan of 12 degrees is equal to H over FB, then FB is equal to H over tan of 12 degrees, and I've got the same thing happening here. And I'm going to tidy that up, and instead of writing tan of 12, I'm going to write cot of 12 degrees. Now I've got an expression for AF and for FB. What do I do with those? Well, I could use Pythagoras here because I know that FB here and FA and the 3 are sitting in a right angle triangle. So that tells me that AF squared plus FB squared must be equal to 3 squared. Now this is going to get a little bit complicated looking. That means I need to square this. Now this is a combined thing. It's got two parts, something times something else. And if you square two things, let me give you an example. Let's say we have AB and we square it. We know that's the square of A times the square of B, don't we? We can raise each of these things to that power separately. So that's what I'm going to do over here. I need to square all of this. And that tells me I need h squared, cot squared 10 degrees. Remember, this is cot 10 all squared, but we put the squared there so that it doesn't look like the 10's been squared. That's just a convention. Now I need to add h squared, cot squared 12 degrees, and all that should equal 9. All right, where do I go from here? Well, I could factorise it, bring the h squared out the front, and I've got cot squared 10 degrees plus cot squared 12 degrees equals 9. Now, these are just values I can get out of my calculator, can't I? So, although it's looking tricky, h squared is equal to 9 divided by all of that. And if h squared is equal to all of that, then h will be the square root of all of that. And I've run out of space here for you to see, so I'm going to take the square root of that side and this side at the same time here. Now, if I put all of that into my calculator, I come out with an answer, which is nice. I get, now it says to do it to the nearest, what is it? How high is the tower? Oh, it doesn't say. So we can choose what we're going to round it off to. It's 0.407 kilometres, that's to 3 decimal places. So it's about 400 metres high, this tower. So 0.407 kilometres, you could keep it in kilometres so it's in the same units here, or you could convert that to metres, whatever you like. So we've found the height of the tower. Now to find what bearing she's driving on. Well, if we now know some things about this triangle, we've got an expression for height, but back here we now have an expression for either FB or AH. We can take whichever one we like, because if we know one of those sides, then we can just use the ratio of it and AB to find theta. Now, rubbing out our original, no, let's move up here to make some space. I'm going to rub out our original picture, just so I can make some room. Now, we've got, let's use FB, because it's right here. Okay, FB equals h cot 12. What's h? Well, we've just found h. So we could say, let's write our trig equation here. We want to know what theta is, and we have this side and this side, so we have opposite and hypotenuse. So we're using sine. Sine of alpha equals FB over 3. So the sine of alpha equals h cot 12 degrees over 3, and the sine of alpha equals, what is h? 0.407. Now at this point you could keep that in your calculator, actually store it using the store function that we've talked about before, and so then when you put this into your calculation it will be the exact value, or you could just keep it in there and hit that answer button, it will do the same thing. So we've got h multiplied by cot 12 over 3. So what's theta? Well, theta is the inverse sine of all of that. And you can put that whole thing into your calculator nice and carefully using brackets and all of this to get an answer for theta, which should come out as